Now, we've had this fascinating conversation that started with pre-training and mid-training. Let's get to post-training. A lot of fun stuff in post-training. So what are some of the interesting ideas in post-training?
The biggest one from 2025 is learning this reinforcement learning with verifiable rewards. You can scale up the training there, which means doing a lot of this kind of iterative generate grade loop. And that lets the models learn both interesting behaviors on the tool use and software side. This could be searching, running commands on their own and seeing the outputs. And then also that training enables this inference time scaling very nicely. And it just turned out that this paradigm was very nicely linked in this, where it's this kind of RL training enables inference time scaling, but inference time scaling could have been found in different ways. So it's kind of this perfect storm of the models change a lot, and the way that they're trained is a major factor in doing so. And this has changed how people approach post-training
Can you
dramatically.
describe RLVR, popularized by DeepSeek R1? Can you describe how it works?
Yeah, fun fact, I was on the team that came up with the term RLVR, which is from our Tulu 3 work before DeepSeek, which is, we don't take a lot of credit for being the people to popularize the scaling RL, but as fun as what academics get, as an aside, is the ability to name and influence the discourse, because the closed labs can only say so much. That one of the things you can do as an academic is, like, you might not have the compute to train the model, but you can frame things in a way that ends up being, I describe it as like a community can come together around this RLVR term, which is very fun. And then DeepSeek is the people that did the training breakthrough, which is they scaled the reinforcement learning, which was you have the model generate answers and then grade the completion if it was right. And then that accuracy is your reward for reinforcement learning. So reinforcement learning is classically an agent that acts in an environment, and the environment gives it a state and a reward back, and you try to maximize this reward. In the case of language models, the reward is normally accuracy on a set of verifiable tasks, whether it's math problems, coding tests, and it starts to get blurry with things like factual domains, like that is also in some ways verifiable, or constraints on your instruction, like respond only with words that start with A. Like all of these things are verifiable in some way. And the core idea of this is you find a lot more of these problems that are verifiable, and you let the model try it many times while taking these RL steps, these RL gradient updates. The infrastructure evolved from this reinforcement learning from human feedback, where in that era, the score they were trying to optimize was a learned reward model of aggregate human preferences. So you kind of change the problem domains, and that let the optimization go on to much bigger scales, which kind of kickstarted a major change in what the models can do and how people use them.
What kind of domains is RLVR amenable to?
Math and code are the famous ones. And then there's a lot of work kind of on what is called rubrics, which is related to a word people might have heard as LLM as a judge, which is like for each problem, I'll have a set of problems in my training data set. I will then have another language model and ask it, what would a good answer to this problem look like? And then you could try the problem a bunch of times over and over again and assign a score based on this rubric. So that's not necessarily verifiable like a math and code domain, but this rubrics idea and other scientific problems that might be a little bit more vague is where a lot of the attention is, where they're trying to push this set of methods into these kind of more open-ended domains where the models can learn a lot more.
I think that's called reinforcement learning with AI feedback, right?
That's the older term from it that was coined in Anthropic's constitutional AI paper. So it's like a lot of these things come in cycles.
Also, just one step back for the RLVR. So I think the interesting, beautiful thing here is that you ask the LLM, let's say, a math question, and then you know the correct answer, and you let the LLM, like you said, figure it out. But how it does it, I mean, you don't really constrain it much. There are some constraints you can add, like use the same language, don't switch between Spanish and English. But let's say you're pretty much hands off. You only give the question and the answer, and then the LLM has to, just the task to arrive at the right answer. But the beautiful thing here is what happens in practice is that the LLM will do a step-by-step description, like, like as a student or like as a mathematician, how you would derive the solution. It will give you, or it will use those steps, and that helps actually the model to improve its own accuracy. And then, like you said, the inference scaling. So inference scaling loosely means basically spending more compute during using the LLM during inference. And here the inference scaling is that the model would use more tokens. And also, I think in the R1 paper, they showed the longer they train the model, the longer the responses are. They grow over time. They use more tokens, so it becomes more expensive. For simple tasks. But these explanations, they help the model with the accuracy. There are also interesting lot of papers showing what the model explains does not necessarily have to be correct, or maybe it's even unrelated to the answer. But for some reason, it still helps the model. Like this is the fact that it is explaining. And I think it's also, again, I don't want to anthropomorphize these LLMs, but it's kind of like how we humans operate, right? If there's a complex math problem, let's say in a math class, you usually have a note paper and you do it step by step, you cross out things, and the model also self-corrects. And that was, I think, the aha moment in the R1 paper. They called it aha moment because the model itself recognized it made a mistake and then said, I did something wrong, and so let me try. And I think that's just so cool that this falls out of just giving it the correct answer and having it figure out how to do it, that it kind of does, in a sense, what a human would do. Although LLMs don't think like humans, it's kind of like an interesting coincidence. And the other nice side effect is it's great for us humans often to see these steps. It builds trust, but also we learn, we can double check things.
There's a lot in here. I think some of the debate, there's been a lot of debate this year on if the language models, like these I think the aha moments are kind of fake, because in pre-training, you essentially have seen the whole internet.
Yep.
So you have definitely seen people explaining their work, even verbally, like a transcript of a math lecture. You try this, I messed this up. And what reinforcement learning is, this RLVR is very good at doing, is amplifying these behaviors, because they're very useful in enabling the model to think longer and to check its work. And I agree that it is very beautiful that this training kind of, the model learns to amplify this in a way that is just so useful at the final answers being better.
I can give you also a hands-on example. I was training the Qwen 3 base model with RLVR on Math 500. The base model had an accuracy of about 15%. Just 50 steps, like in a few minutes with RLVR, the model went from 15% to 50% accuracy. And the model, you can't tell me it's learning anything about fundamentally about math.
The Qwen example is weird because there's been 2 papers this year, one of which I was on, that talks about data contamination in Qwen, and specifically that they train on a lot of this special mid-training phase that we spent like a minute on, because it's weird. And so they train on problems that are almost identical to math.
And so you can see that basically the RL, it's not teaching the model any new knowledge about math. You can't do that in 50 steps. So the knowledge is already there in the pre-training. You're just unlocking it.
I still disagree with the kind of premise, because there's a lot of weird complexities that you can't prove, because one of the things that points to weirdness is that if you take the Qwen 3 so-called base model, and you could Google on the screen, you could Google like math dataset Hugging Face, and you could take a problem, and what you do if you put it into Qwen 3 base, all these math problems have words. So it'd be like, Alice has 5 apples and takes blood and gives 3 to whoever, and there are these word problems. With these Qwen-based models, why people are suspicious of them is if you change the numbers but keep the words, Qwen will produce like a very high, without tools, will produce a very high accuracy, like decimal representation of the answer, which means there's some like, at some time it was shown problems that were almost identical to the test set, and it was using tools to get a very high precision answer. But a language model without tools will never actually have this. So it's kind of been this big debate in the research community, is like how much of these reinforcement learning papers that are training on Qwen and measuring specifically on this like math benchmark, where there's been multiple papers talking about contamination, is like, how much can you believe them? And I think this is what caused the reputation of RLVR being about formatting, because you can get these gains so quickly, and therefore it must already be in the model. But there's a lot of complexity here that it's not really like controlled experimentation, so we don't really know.
But if it weren't true, I would say distillation wouldn't work, right? I mean, distillation can work to some extent, but the thing is, that is, I think, the biggest problem in LLM research, this contamination, because we don't know what's in the data. It's unless you have a new data set, it's really impossible. And the same, you mentioned math, the math data set, which is you have a question and an answer and an explanation is given. But then also even something simpler like MMLU, which is a multiple choice choice benchmark. If you just change the format slightly, like, I don't know, you use a dot instead of a parenthesis or something like that, the model accuracy will vastly differ.
I think that could be like a model issue rather than a general issue.
It's not even malicious by the developers of the LLM, like, hey, we want to cheat at that benchmark. It's just, it has seen something at some point. And I think the only fair way to evaluate an LLM is to have a new benchmark that is after the cutoff date when the LLM was deployed.
Can we lay out what would be the sort of the recipe of all the things that would be going to post-training? And you mentioned RLVR was a really exciting, effective thing.
Mm-hmm.
Maybe we should elaborate. RLHF still has a really important component to play. What kind of other ideas are there on post-training?
I think you can kind of take this in order. I think you could view it as what made O1, which is this first reasoning model, possible, or what will the latest model be? And they actually have, you're going to have similar interventions at these, where you start with mid-training, and the thing that is rumored to enable O1 and similar models is really careful data curation, where you're providing a broad set of like what is called reasoning traces, which is just the model generating words in a forward process that is reflecting, like, breaking down a problem into intermediate steps and trying to solve them. So at mid-training, you need to have data that is similar to this to make it so that when you move into post-training, primarily with this verifiable rewards, it can learn. And then what is happening today is you're figuring out which problems to give the model and how long you can train it for, and like how much inference you can enable the model to use when solving these verifiable problems. So as models get better, certain problems are no longer, like, the model will solve them 100% of the time, and therefore there's very little signal in this. If we look at the GRPO equation, this one is famous for this because essentially the reward given to the agent is based on how good a given action is a completion, is relative to the other answers to that same problem. So if all the problems get the same answer, there's no signal in these types of algorithms. So what they're doing is they're finding harder problems, which is why you hear about things like scientific domains, which is like, that's so hard, like getting anything right there. If you have a lab or something, it just generates so many tokens, or much harder software problems. So the frontier models are all pushing into these harder domains, and they can train on more problems, and the model will learn more skills at once. The RLHF link to this is kind of like, RLHF has been and still is kind of like the finishing touch on the models, where it makes the models more useful by improving the organization or style or tone. There's different things that resonates to different audiences. Like, some people like a really quirky model, and RLHF could be good at enabling that personality. And some people hate this like markdown bulleted list thing that the models do, but it's actually really good for quickly parsing information. In RLHF, this human feedback stage is really great for just putting this into the model at the end of the day. So it's what made ChatGPT so magical for people. And that use has actually remained fairly stable. This formatting can also help the models get better at math problems, for example. So it's like, the border between style and formatting and like the method that you use to answer a problem is actually, they're all very closely linked in terms of when you're training these models, which is why RLHF can still say make a model better at math, but these verifiable domains are a much more direct process to doing this, because it's kind of makes more sense with the problem formulation, which is why it kind of ends up all forming together. But to summarize, it's like mid-training is give the model the skills it needs to then learn. RL and verifiable rewards is let the model try a lot of times. So put a lot of compute into trial and error learning across hard problems. And then RLHF would be like, finish the model, make it easy to use, and kind of just round the model out.
Can you comment on the amount of compute required for RLVR?
It's only gone up and up. So I think Grok 4 was famous for saying they use a similar amount of compute for pre-training and post-training. Back to the scaling discussion, they involve very different hardware for scaling. Pre-training is very compute bound, which is like this flops discussion, which is just how many matrix multiplications can you get through in one time. And because RL, you're generating these answers, you're trying the model in the real world environments, it ends up being much more memory bound because you're generating long sequences, and the attention mechanisms have this behavior where you get a quadratic increase in memory as you're getting to longer sequences. So the compute becomes very different. So when in pre-training, we would talk about a model, I think if we go back to like the Biden administration executive order, it's like 10 to the 25th flops to train a model. If you're using flops in post-training, it's a lot weirder because the reality is just like, how many hours are you allocating how many GPUs for? And I think in terms of time, the RL compute is getting much closer because you just can't put it all into one system. Like pre-training is so computationally dense where all the GPUs are talking to each other and it's extremely efficient, where RL has all these moving parts and it can just take a long time to generate a sequence of 100,000 tokens. Like if you think about GPT 5.2 Pro taking an hour, it's like, what if your training run has a sample for an hour and you have to make it so that's handled efficiently? So I think in GPU hours or just like wall clock hours, the RL runs are probably approaching the number of days as pre-training, but they probably aren't using as many GPUs at the same time. There's rules of thumb where in labs, it's like you don't want your pre-training runs to last more than like a month because they fail catastrophically. And if you were planning a huge cluster to be held for 2 months and then it fails on day 50, the opportunity cost is just so big. So you kind of don't want to people don't want to put all their eggs in one basket, which is like GPT-4 was like the ultimate YOLO run and nobody ever wanted to do it before, where it took like 3 months to train and everybody was shocked that it worked, where I think people are a little bit more cautious and incremental now.
So RLVR is more, let's say, unlimited how much you can train and get still benefit, where RLHF, because it's a preference tuning, you reach a certain point where it doesn't really make sense to spend more RL budget on that. So just a step back with preference tuning. So there are multiple people that can give multiple, let's say, explanations for the same thing, and they can both be correct. But at some point, you learn a certain style, and it doesn't make sense to, iterate on it. My favorite example is like if relatives ask me what laptop they should buy, I give them an explanation or ask them like, yeah, what is your use case? Like they, for example, prioritize battery life and storage. Other people like us, for example, we would prioritize RAM and compute. And so, but both answers are correct, but different people require different answers. And with preference tuning, well, you're trying to average somehow. Like you are asking data labelers to give you the right, or not the right, the preferred answer, and then you train on that. But at some point, yeah, you learn that average preferred answer, and there's no, I think, reason to keep training longer on it because it's just a style. Where with RLVR, you literally give the model. Well, you let the model solve more and more complex, difficult problems. And so I think that it makes more sense to allocate more budget long-term to LRVR. And also that right now we are in LRVR 1.0 land, where it's still like that simple thing where we have a question and answer, but we don't do anything with the one stuff in between. So there was multiple research papers also by Google, for example, on process reward models that also give scores for the explanation, how correct is the explanation. And I think that will be the next thing, let's say RLVR 2.0 for this year, focusing in between question and answer, like how to leverage that information, the explanation, to improve the explanation and help it to get better accuracy. But then, so that's one angle. And there was a DeepSeek Math version 2 paper where they also had interesting inference scaling there, where, well, first they had developed models that grade themselves, a separate model. And I think that will be one aspect. And the other, like Nathan mentioned, it will be for LRVR branching into other domains.
The place where people are excited are value functions, which is pretty similar. So process reward models are kind of like process reward models assign how good something is to each kind of intermediate step in a reasoning process, where value functions apply value to every token the language model generates. Both of these have been largely unproven in the language modeling or this reasoning model era. People are more optimistic about value functions for whatever reason now. I think process reward models were tried a lot more in this pre-01, pre-reasoning model era, and a lot of people had a lot of headaches with them. So I think a lot of it is the human nature of like value models have a very deep history in reinforcement learning. They're one of the first things that were core to like deep reinforcement learning existing, is like training value models in this. So right now the literature, people are excited about trying value models, but there's very little proof in it. And there are negative examples in trying to scale up process reward models. These things don't always hold in the future. I think we came to this discussion by talking about scaling. And a simple way to summarize what you're saying with like you don't want to do too much RLHF, which is essentially the signal scales, is people have worked on RLHF for language models for years, especially an intense interest after ChatGPT. And this the first release of a reasoning model trained with RLVR, OpenAI's O1, had a scaling plot where if you increase the training compute logarithmically, you get a linear increase in evaluations. And this has been reproduced multiple times. I think DeepSeek had a plot like this. But there's no scaling law for RLHF where if you log increase the compute, you get some performance. In fact, the seminal scaling paper for RLHF is scaling laws for reward model over optimization. So it's like that's a big line to draw with RLVR and the methods we have now and in the future. Like they will follow this scaling paradigm, which is like the best runs you can let to run for an extra 10x and you get a few x performance, but you can't do this with RLHF. And that is just going to be field defining in how people approach them, where I'm a shill for people academically to do RLHF. And that's a good way to describe it, is like to do the best RLHF, you might not need the extra 10 or 100x of compute, but to do the best RLVR you do. So I think there's what I say is a seminal paper from what was a meta internship. It's like the art of scaling reinforcement learning with language models. What they describe as a framework is scale RL, and their incremental experiment was like 10,000 B200 hours, which is like thousands or tens of thousands of dollars per experiment. And they do a lot of them, which is just like, this cost is not accessible to the average academic, which is a hard equilibrium where it's trying to figure out how to learn from each community.